is discussions I had with students at Carnegie Mellon, and I realized that they're younger than me, and most of them do not know the history of computing, shall we say, before you were born, okay? So we're going to start with the earliest academic computing, say what it would have been like to have used various forms of computing up to about 1995 or thereabouts, okay? This slide shows the very first computer that I ever programmed in about 1962, I think. It's a Ferranti Pegasus computer, and I'm not going to tell you anything about that. This is, of course, a more recent computer. It's the computer that I program on today. What I'm going to do is I'm going to skip that very early, and I'm going to start in the late 1960s. Interestingly enough, as an undergraduate, I was a mathematics major, and I never went anywhere near a computer. You didn't need a computer to do mathematics. In fact, there weren't any computers, whatever your field was. I started doing serious computing as a master's student, and I call this the age of dinosaurs, okay? And this is a typical dinosaur of that era. Notice in the front here, magnetic tapes. This was where we stored large amounts of data. These huge boxes in the back, one or two of them are the central processors. This thing down here is a primitive disk drive. You can see how big it is. It had about 10 megabytes of data. By the way, this is an IBM 360. The successors of this computer are still being used today. Even IBM calls them dinosaurs, and there's a reason for that. In order to understand this story, we've got to think about hardware, okay? It's almost impossible to describe how slow and expensive computers were in those days. One little factoid, for a machine like that, memory cost $1 a byte, okay? So this computer has 8 gigabytes. The memory, that amount of memory would have cost $8 billion in the late 1960s. Everything we did in those days was dominated by the huge cost of computing and the need to somehow or other share it, okay? There's a second thing that's really important and is not often talked about, and that's economies of scale. One big computer gave you a lot more bang for your buck than 2 medium-sized computers. And therefore, every organization followed the same strategy. You buy the biggest computer you can afford, you create a computer center to run it, and you find ways to share the capacity amongst your various users. And those ways of sharing the capacity might be system software, there might be operating procedures, there might be charging schemes, but somehow or other you had to share a very scarce resource amongst people who wanted much more. And these machines were too expensive. My guess is that Williams College could not afford its own computer until about 1980, but certainly in the early days these machines were too expensive for small or medium-sized organizations. A little tiny bit more about them. I've already pointed out the use of magnetic tapes for backing store and the small disks. To get data into the computer, we used punch cards. I'll show you a little bit about punch cards. Somebody asked a question earlier. That Pegasus computer was before punch cards, but punch cards were standard for quite a long time. The only way to get output out was a shared central printer, okay? Communications, notice what it says about communications. No communications. These were freestanding computers. So when I was doing my master's degree at the London School of Economics, what we did was wrote our programs, Fortran programs. We're actually doing statistics and those sorts of things. We wrote them on pieces of paper, we handed them in, and a data processing clerk typed them onto punch cards. By the way, they were all women. It was just a fact of life. So here's a punch card, okay? What you do is you take a typical column there. Each column represents a character. So 80 column punch cards, 80 characters, and the pattern of holes represents an A or a 1 or some other character. So that was the only way we could get our data into the computers. and if you made a mistake, you had to repunch the card. This was how business computing was done for a surprisingly long time. But what's interesting about these computers, the IBM 360, which was the sort of the definitive computer of that era, was definitely built for businesses, commercial organizations. And universities were very different from commercial organizations. The typical business had a small number of large jobs. Today is Friday afternoon we run payroll, okay? And the jobs were all run by professionals. There were professionals who typed the cards, professional operators who put them in the computer, professionals who took the paper off the line printers, chopped them up, put them in envelopes and mailed them out or so forth. Universities are very different. In university, our pattern of use is we have many independent users, students, faculty members, researchers, okay? We have many small jobs. A lot of jobs are writing programs, trying to work out why they don't work, writing them again and so forth. And so we very rapidly moved to what can be called end-user computing. That is where the actual person doing the work, the student or the faculty member, actually did the computing. And this is very, very different from the picture before where you saw the photograph of the clerk typing the punch card. So universities went off and developed very different computer systems from those used by commerce. And we were pioneers in a number of things that actually became mainstream and were adopted by the commercial sector later. Here are some of them. End-user computing, and I'm going to talk about time sharing, okay? Decentralized decision-making. These centralized computers, these big machines with their computer centers lend themselves to central decision-making, okay? As the person in charge of computing at, shall we say, Dartmouth College, as I was, I had the only computer, okay? And I made all the decisions, and people had to put up with them. But we rapidly moved towards decentralized computing, where individuals had or departments had their own computers. And technically, those were mini computers and personal computers. A lot of the history of small computers comes through education. Distributed computing, linking these small computers together and the networks to put them together. All of these areas, universities were ahead of the commercial mainstream. And if you understand the different needs, you'll understand why. Okay, this is the second of 4 black and white pictures I'm going to show you showing somebody with their hands on a keyboard, okay? This one differs from the previous one in a very fundamental way. The person with his hands on the keyboard is an end user, a student. This is not a clerk, this is the actual person doing the work. It's a Dartmouth student from the late 1960s, okay? What he's using is a so-called teletype terminal. The keyboard, you type a character on the keyboard. This is not a computer. There's no electronics in this device at all. You type a character on the keyboard, the character is transmitted over a telephone wire to a central computer. That's the only way you can get data into the computer. If the computer wants to get data out, it sends characters back over that wire and they're printed on the terminal. So it's a terminal being used to type information into a central computer. But it's the end user doing it. Time sharing was basically a system that allowed large numbers of people. The Dartmouth time sharing system, we used to run about 200 people simultaneously. And the aim is to give each of those people the impression that they have sole use of a medium-sized computer. In fact, they're sharing it with others, but the whole design of the system was to try to give them enough of a computer that they felt that they would by themselves, okay? So each user had a terminal, a share of the central processor, a technique called time slicing. If you were running a job, you might have 1/10 of a second, and then you had been interrupted, and the next person in turn would have it for 1/10 of a second, and so forth. And you'd have all your jobs would be sitting in memory, so because memory was expensive, your jobs had to be pretty small. During my PhD thesis in the late 1960s, I was allowed as much computer time as I could use so long as I didn't use more than 24 kilobytes of memory, okay? How it was done is quite interesting. But you had an allocation of memory. Your job sat in memory, and when your turn came, you ran for a while until interrupted. There was also central disk store. Disks were beginning to become available, expensive but available. And the disk store was used for two purposes. One is used for your private files, so you could leave your data there when you did something else. But the other thing it was used for was a central file system, a shared file system. So nowadays, if we are, if you're running a course, I might put my course materials on a website or on a specialized shared central system. In those days, we put our course materials onto the time-sharing system, central computer, and programs, data, lecture notes, and things like that. So this shared data was a very important and early use of these systems. The other thing that Dartmouth is well known for is the fact that these end users, and the emphasis was not on skilled professionals. So there were similar systems developed at, say, MIT or Cambridge University in England, designed for researchers, specialists. Dartmouth's whole emphasis was on people who didn't do much programming. Or computing. Very early on, there was a requirement made by the mathematics department that everybody who took a mathematics course, every student had to be able to prove they could write a small program. Interestingly enough, it was very clearly stated the faculty didn't have to pass this test, but the students had to. For that reason, Dartmouth developed a number of things, and I do say Dartmouth here as opposed to the other systems, that you need for end users. First of all, very simple commands. So if you wanted to create a new file, you typed new in the file name. If you wanted to run a program, you typed run. And simple error messages. No such file, for example. On a commercial operating system, an error message might be of the form 4JWX, and you were expected to look that up. The idea that they were actually human readable was a breakthrough. And help systems. Help systems we take for granted now. Help systems were invented at some stage. Dartmouth is best known for having invented a very simple programming language called BASIC. The whole idea of BASIC was it was designed for people at that sort of terminal to be able to write simple programs. And actually, as time went on, the language got extended. Notice, by the way, the line numbers here. The reason for the line numbers is if you wanted to change a line, you wanted to edit a line, on those teletype terminals, the much easiest thing to do is just to retype the line, type in a new line. And so if I wanted to replace line number 30, I'd just type it in again. BASIC, because it's a very simple language to learn, easy to implement, very efficient on small computers, had an interesting history of being the first language on the first mini computers and the first language on the personal computers. Bill Gates got his start writing a BASIC interpreter for a long dead microcomputer. So in time sharing, fascinating part of computing history, basically done by universities. And because of it, universities were the first people to do computer networking, starting with very primitive connect terminal to central computer. Support for end users, I've shown you some of those. And we were the first people to have to face up to the problems of system security. When you've got a university with a few thousand people, there'll be somebody out there who's trying to break system security, okay? And people did. One of our students who was very successful and very clever at breaking the Dartmouth system has written one of the standard textbooks on system security. So poachers make the best gamekeepers, as they say. The MIT system, which was a very fine system, called Multics, is very important because it was very much involved with the development of the theory of operating systems, particularly the UNIX operating system. You're probably familiar with the Linux operating system, which is the modern version of UNIX. That was developed by Bell Labs with a lot of input from MIT. Dartmouth's command language and BASIC were used in a whole family of mini computers, personal computers, and I'm told, though I haven't seen the film, that it's also used by the robot HAL in the film 2001 A Space Odyssey. If anybody's seen that film and would like to help me with that, that's great. So time sharing, we were very proud of time sharing. It was technically a superb achievement, but there were many things about time sharing that didn't quite work. The first thing was, it was a uniform service for everybody, and everybody's not uniform. The people at universities do all sorts of different things, but we had to give everybody the same service. There was never enough resource. We never had enough computing power, we never had enough memory, we never had enough disk storage. And finally, we could only run programs that were written specifically for that computer. And interestingly enough, statistics was one of the major problems. So the early statistics programs, SPSS and SAS, were beginning to get very important in the field of applied statistics, and we couldn't run them because they weren't written for our computer. So despite this being a really great system, there were things wrong with it. The next things were mini computers. This is a VAX 11780 mini computer by Digital Equipment Corporation from outside Boston, otherwise known as DEC. Very, very important computer in the history of computing. Mini computers were possible because the economies of scale started breaking down. And by the late 1970s, there were these powerful mini computers which for some tasks were actually more cost effective than the big mainframes. My guess is that when Williams College first had a university computing service, it was either on a VAX 11780 or on another large mini computer of that generation. I don't know if there's anybody here who goes back far enough. But that was these were good, fast computer systems that had a lot of uses in smaller organizations. They were also, the smaller mini computers could be used for dedicated tasks, like computer graphics, where you can't wait for your turn. They've got to be interactive. So mini computers were really important. From an organizational point of view, they were fascinating because mini computers are naturally owned by departments or individuals or research groups. And if you think of this centralized organizational structure that we had for computing, there was this great tension, and in some places there was a really severe tension between the departments who wanted to go their own way and the central computing people who felt for the good of the organization we need to control everything that's going on. Fortunately, I learned very early on a principle of life that is if you can't beat them, you better join them. And I was always an advocate for decentralization supported by the central things. That's probably why I managed to keep my job longer than some of my colleagues. Okay, let's move on. Microcomputers, personal computers. Okay, this is a chip. It's an Intel 8088 chip. Famous because when IBM decided in about 1970, 1971 to build a personal computer, this is the one they chose. There's no particular reason why they chose this one, but because they chose that one, it's been the base, the Intel family of chips has been the basis for most personal computers ever since. These were powerful enough that it was possible, and memory also becoming cheap enough, it was possible to build personal computers. And the personal computer that really had its big impact in universities and actually in all forms of education was the Apple II. First time that Steve Jobs' name appears. One of my colleagues said about Steve that he was the first person to think of a computer as a fashion item. And those of you who've got iPad 6s and 7s and 8s and 9s, iPhone, the latest iPhones understand the fashion part of computing, okay? Keyboard, processor, a screen with some reasonable graphics. These boxes on the right are so-called floppy disks. Here's a floppy disk. Inside that paper envelope, there's a magnetic disk, okay? These magnetic disks were the only backing store. There was no hard disk on this. But they were very, very important because, look at this. Here we have somebody selling a software program. So this is where the consumer software industry started. People wrote programs, put them on floppy disks, put them in a box with a manual, and started selling them. And this selling software, so that you didn't have to write every program locally, was really what made the Apple II and similar computers successful. This, by the way, is a flight simulator, which some of you may recognize. Microsoft later took over this company, and it became the Microsoft Flight Simulator. The Apple was a bit of a fly-by-night company. It was IBM's acceptance of personal computers that made personal computing respectable. Okay? And this is an IBM PC from about 1981. Sorry, did I say 71 earlier when I talked about the 88? About 1981. And I had a computer very much like this one. You see the computer, you see the screen with very poor user interface. You see a first personal printer, and these were the machines that really took over business. A little bit of detail about these machines. I won't go into much of it. Very limited communications. I want to stress that part. Memory growing. I had 128K, the big IBM personal computer. The reason I had the big one was so I could run the Pascal compiler. Okay. And incidentally enough, they came with the basic programming language built in and the world's crudest user interface on Microsoft DOS. It's difficult to explain just how bad a user interface Microsoft DOS had in its early days. It's important though, okay? And the software market. These personal computers created a dilemma for universities. First of all, remember our three problems. One is all users are not the same. Different personal computers with different software meant one could have different users having different computers. That was good. The capacity problems were partially solved by the people with money bought their own machine or their small mini computer. And programs did not have to be written locally. So they went quite a long way towards solving our problems. But unfortunately, they came with their own problems. The first was the user interface was pathetic. And I can't stress this too much. We'd worked so hard getting good user interfaces onto our time-shared systems. We didn't want to go backwards, okay? They were much too slow for scientific calculation or data manipulation. By this stage, our central computers were getting quite good at those things. And there was no way of sharing data. We lost our central file system. Finally, there's the organizational thing. And sometime I'd like to just talk about the organizational things because if ever you get a career in technology, you'll find organizational issues are much, much, much more important than you ever taught as a student, okay? We've just about got to grips with the idea of a central computing center, a few departments, strong, well-supported departments running their own computers. But now every single faculty member had their own idea of their own, they buy their own computer and do silly things and expect to be supported by the central organization. Many central computing organizations thought that their job was to protect their university against this proliferation of scruffy little computers, okay? Two strategies came out of this, and I was involved with both of them. Here's the one we did at Dartmouth. This is my third photograph of student with fingers on the keyboard, okay? This is the first time we have a politically correct photograph showing a man and a woman. But I won't go on to that point. But anyway, this is a very early Macintosh, okay? And the idea was that the Macintosh could be used as a terminal, okay? Or as a freestanding computer. So the strategy was encourage everybody to have their own Macintosh computer, use the personal computer as a personal computer for simple things like word processing and editing files and spreadsheets and so forth, but also make it into a good terminal so that for things that required more calculation or sharing data, the students had a good terminal. You could understand behind this that meant we had to have a campus network so that they could do that, and we had to do a lot of networking, which was another area where the universities were pioneers. This was not a need that the people in industry had. We chose the Macintosh because it has a user interface that was better than we were able to provide on time sharing. As the provost at the time said, that's a computer that the humanities faculty might enjoy using. And that was really the definitive, I might say in passing, there's a computer that I might enjoy using too. I've had essentially every Macintosh ever built, and I had, before the Macintosh, there was a computer called a Lisa, and they had 4 models of the Lisa, and Steve Jobs told me I was the only person he'd ever met who had had all 4 of those models. So you can understand I was an advocate for this strategy. Here's a screen dump of a Macintosh being used as a terminal in those early days. Notice there are 5 windows there open. The ones labeled D1 and D2 are copies. At that time we were running the Dartmouth time-shared system on 2 separate computers. There's a computer called U2, which was a UNIX, V1 was a VAX, and the one, CMS1, was actually an IBM machine. So 4 terminal sessions at the same time on the same little Macintosh. Primitive by today's standards, we thought this was really, state of the art. It was state of the art at the time. So that is the personal computer as a terminal. The next stage in the history is shown by this one, Carnegie Mellon University. This is a Carnegie Mellon student in the around about 1986, I think. No, it'd be about 1987. Sitting at a big personal computer. The big difference here is this personal computer is powerful enough that this student can do almost all his work at this computer. So we've gone from the personal computer as a terminal to the personal computer as where you do your work. There's a strong network behind this, but the networking is supplementary. Most of the time you're writing your programs, running your programs, doing your text editing, doing your data manipulation on the personal computer. And those personal computers used to be called workstations. Here are a few more of them from the late 1980s. All of these ones had a lot of university input. The one at the left is one of the few computers, early computers, that I never had one of my own, and that's a Sun 1. I only had a Sun 2. I always feel a bit left out on that. Sun, as many of you will know, was for many years the leading manufacturer of large Unix-based workstations. Sun stands for Stanford University. The hardware was developed in-house at Stanford, and the software came from Berkeley UNIX. So very much a university-built system. The one in the middle is a DEC VAX station. So DEC Digital Equipment Corporation, who made those big VAXes, 10 years later had a workstation, and this small workstation was about as powerful as that big VAX that I showed you before. The problem that DEC is a lovely machine, but DEC got all tangled up because by selling this aggressively, they were going to lose their market for the other machines. They've messed things up so completely that within a decade, DEC, which had been the second biggest computer company in the world, was bankrupt. Okay, shows what a challenge these things are. The one on the right was the sort of queen of these workstations. It's a Next workstation. Steve Jobs was thrown out of Apple about 1985 for being a jerk. Okay, he was a jerk. He deserved to be thrown out. He was insufferable. When he was thrown out, he came and he actually hid away in a house that we had for guests at Carnegie Mellon University. I lived in the same house at the time because I was just arriving at Carnegie Mellon. That's how I got to work with him and worked on this machine. There's a lot of Carnegie Mellon technology in this machine. And the operating system they developed for this machine, which is a version of Unix, is fundamentally the operating system that runs on this machine today. So there's a direct continuity. Lovely machine, total failure in the marketplace. And for reasons that I won't go into. Pressing right along. I've mentioned Unix. Berkeley Unix, in particular, very, very important in the history of computing. Unix itself, as I mentioned, was developed at Bell Labs as an operating system for small computers, PDP-11 mini computers. The University of California at Berkeley got a contract, a government contract, to expand UNIX, make an open source version with a lot of modern features, operating system features in it. The name associated with this is Bill Joy, who was one of the founders of Sun. Very, very important feature. There are two very important features of this. One is open source. The Berkeley open source software license is about as open as any license can be. It says, here it is, do whatever you want with it. And in the version known as 4.2, they were paid to incorporate the protocols known as TCP/IP, which you may know as the underpinnings of today's internet. Berkeley's contribution we cannot underestimate Berkeley's contribution. Almost all the early workstations use some version of Berkeley's BSD, and the TCP/IP code that they wrote was picked up by everybody, and it's the reason that the internet spread so quickly when it spread was because those protocols were available with open source implementation. Turning these big personal computers into an environment for a large organization, such as a university, was a serious challenge. And there were two very big projects at the time. There was the Andrew project at Carnegie Mellon, where we had enormous support from IBM, and MIT, not to be outdone. IBM always refuses to admit to coming second in any of these things, and actually MIT has been a phenomenal contributor to these things. They had a similar project called Athena, which was supported by both IBM and Digital. The projects actually were quite similar. Of course, at the time, we made a lot of the difference, but actually they were similar. The strategy was simple. Everybody has a workstation, powerful machine. They all run the same operating system, and we standardized on Berkeley UNIX. Almost all the work is done on the workstation, but they're connected to a high-speed network, and the network has shared services on it. And the thing we did particularly at Carnegie Mellon was to develop a very high-performance file system to be shared across the things. So just to give you an example of what is necessary for a university to do, we developed the graphical user interface, a distributed file system, the campus network, email and bulletin boards, which were just beginning to get going. When I joined Carnegie Mellon in 1985, there was no way we could send an email message between Dartmouth and Carnegie Mellon because we used different email systems. A few years later, it was standard. And we put a lot of money and effort into advanced educational applications. One of the boldest things I ever did in my life was, having said we're going to provide such a fine workstation environment, we're not going to need time sharing. In 1987 or 8, I'm not quite certain the exact date, but I think it was the 1st of January 1988, we actually turned off our central mainframe computers. This, I believe, we were the first substantial organization in the world to run their computing without a central mainframe computer. And we got away with it. I mentioned the distributed file system. This is the Andrew file system at about that time. Each of those racks is a Sun 2 workstation with 3 or 4 large disk drives. We used to run this machine room with the lights turned off, okay? No operators at all. Nowadays, we'd call this a server farm. This is the early, and I believe the first modern server farm. That is a file system consisting of a large number of small computers, which just looks like one large file system to the users. Okay, the Andrew project at Carnegie Mellon. We were very proud of Andrew. We did a lot of good work, and it's a fine system, but it wasn't perfect. And there were 3 reasons. You may recognize these same 3 reasons, okay? First reason is that it assumed that all users were the same, and all users are not the same, okay? Secondly, we never had enough capacity. Even if people were buying their own workstations, the capacity of the network, the capacity of the file system and things slowed down things. Finally, we were unable to run programs that hadn't been written for BSD Unix. Interestingly enough, the statistics packages like SPSS and SAS were important ones there. Okay? So what we did was we came up with, and this is, I think I can claim that this was my strategic contribution to this. I call it Andrew Plus. If you notice up there, we have a Unix workstation. In the middle, we have a data network. We didn't call them clouds in those days. Okay? Bottom, we have services. Andrew file system, Andrew printing, Andrew mail. But also on this diagram, we have other services which are not part of the Andrew system, a library system, administration systems, a supercomputer. And across the top, we have other types of computers. Even while we were building this fine Unix-based environment, IBM was giving us lots of personal computers to run their DOS, and individuals were buying thousands of Macintoshes. So it was this if you look at this environment, this is the environment you have today, okay? Today what you have is you have a network. It's called the internet, okay? And you have a campus version, a campus extension of the network. You have a variety of computers. And you have a variety of services. And by using standardized protocols and formats and things like that, any one of these computers can make use of any one of these services. So although this is where I end my story, but I think you can understand this is where the modern computing environment really became stable. And I want to just mention two things. One is the need for a campus network. You've seen campus networking everywhere. Universities were way in advance of the commercial sector in campus networking because we wanted the network to go everywhere, and we assumed that there would be equipment from lots of different vendors, not just from one vendor. So IBM had their networking system, but it was designed to connect IBM machines together. Digital DEC had their own system. It was designed to connect digital things together. We were the first people to connect heterogeneous things together, and that's where the TCP/IP work at Berkeley and other places was so important. For example, MIT were the first people to run TCP/IP on an IBM PC. We were at Carnegie Mellon, we were the first people to run TCP/IP on VAX stations, and so forth. Oh, and by the way, Stanford and Carnegie Mellon worked together. We were the first people to generate IP addresses dynamically, so that when I come here and I plug my machine in, I get a network address automatically. I don't have to be given a hard network address. Two quick slides. Here is the Dartmouth network, an example of what you could do with a Macintosh about 1986. This was after I left, a little bit after, but what you see there is various network services available from your personal computer. And here's a picture of the Carnegie Mellon system, which is pretty close to what you have in today. The key thing is a standardized wiring system throughout in the buildings, and these things called routers, which pass messages to and fro. I mentioned a little bit about the impact. I've already mentioned the top 2 or 3 things here. The fact that we were doing the TCP/IP networking led to its adoption for the National Science Foundation's supercomputing network, which became the basis of the national and international internet. We had to build all these components. So there's routers, which on the diagrams we built. We built the hardware, we built the software, okay? Nowadays you get commercial, and you may well get it from Cisco. Cisco is a company that started with a stolen version of Stanford's networking software, and some court cases involved. Okay, I'm running out of time. In the 1990s, university computing and business computing converged. And the reason was the businesses started using end-user computing. They started using end-user computing, and they started using the internet. I remember a meeting with the Alcoa computing people in about 1988 or 9, trying to persuade them that the future of computing was in network and heterogeneous computing, and getting absolutely nowhere. They thought I was a long-haired, bearded intellectual. And, well, I had a beard, but apart from, but the point about it is, things which we take for granted then were not part of their world. Computing industry supports the businesses, so they started producing products. The software that we ran were getting more and more complicated. The Dartmouth system was written by undergraduates, believe it or not. The Carnegie Mellon system was written by a group of maybe 30 PhD-level computer scientists. Nowadays, you have thousands. A friend of mine was in charge of the development of Windows XP. He had 25,000 people working for him. Okay? Universities can't do this. Finally, in the dot-com boom, about year 1999 and 2000, many of our best staff left and got rich. The networking group at Carnegie Mellon all went to Silicon Valley, and essentially all of them made a lot of money. And good luck to them too. They were first-rate, hard-working people, and they deserved it. So today, as universities, we rely almost entirely on commercial products. Everything I'm using now, from the computer to the network to the projectors, is a commercial product. And they're good commercial products. But there's a part of history in which the universities were actually leading and the commercial companies were catching up. Okay, if you want to learn more about this, I started writing, and John, this will amuse you, I started writing an abstract for Phi Beta Kappa with the idea of writing 150 words, and I ended up writing 20,000 words. And if you search by this title, you'll find them. So there we have it. The dinosaur and the apple, okay? Both of these were gifts to me from the companies. IBM, you know, this dinosaur was a gift from IBM. They understood where things were going, and I'm very proud of that apple, which was given to me at Dartmouth in about 1985. Okay, a little bit of time left. Sorry to go so quickly through all of this. You'd be surprised how much I left out. Almost every slide could have been a 2-hour lecture. But just to tell you a little bit about how we got to the sort of computing that you take for granted. Maybe 30 years from now, one of you will be standing up and talking to another group of students and explaining to them what primitive computing we had in 2015 and how they don't realize how they got to where it is. Can I ask for questions? Observations, disagreement, criticism?
So just before...
Bill, I'd be interested to know, in view of the account you've given of the sort of interplay of the dynamism between the universities and business corporations, whether the structure of that relationship looking forward in the decades ahead is going to be a symbiosis that produces similar advance, or are there risks in the way that relationship may develop that could impede progress?
Would you like to answer that question? I mean, I have the faintest idea. What I do know is there's this huge difference between, in the times I'm talking about, if you had an idea of something that needed to be done, you did it, okay? Now, if you have an idea of something that needs to be done, you go and find a venture capitalist and create a company. Stanford was the real pioneer of this. It was very obvious. They didn't, you know, Stanford's name doesn't appear much in this story, apart from in 2 cases. One is the Sun Workstation, and the other is Cisco. Both are examples of they started doing something great and immediately spun off companies. And now, and this immediately spinning off companies, it's a different mindset. And right now, I don't see much creativity in universities in developing the software, the systems. There's a lot of creativity in universities in doing fundamental research. Most of the work in which the technology behind somewhere like Google or Amazon is coming out of computer science departments. And there's universities are creative places, so there's interesting applications being done everywhere. But this building the actual systems doesn't seem to be part of universities these days, for good reason.
So if there are additional questions, we will stay around here for a couple of minutes. There will be several other activities for the Phi Beta Kappa 150th anniversary today. If anybody's interested, there is lunch in the faculty house at noon. Just say you're with Phi Beta Kappa unless you want to pay for yourself. At 4 o'clock in Griffin 3 or 4, depending on how many people show up, we will have a series of talks from 4 to 7:30 with wine, cheese, pizza, and a cake. And so I hope you can join us for some of that and stay around for a little bit. So let's thank our speaker.